of X is called resolvent set of X. Resolvent set of X. The theorem. Theorem. Now, sigma of X is a closed subset of the graph. Sigma X is a closed subset of the graph. Graph. Found symbol. The graph. Further, norm X. Further, norm X less than mod Y. That implies lambda belongs to rho of X. Rho of X. And hence lambda belongs to rho of X. That implies modulus of lambda is less than or equal to norm X. So let sigma of X denote the closure of rho X. Denote the rho of X. Rho of X. Denote the closure of denote the closure of sigma X. Closure of sigma X. Then lambda belongs to lambda belongs to lambda belongs to rho of X. That implies there exists lambda n subset rho of X belongs to lambda n tends to lambda. That implies X minus lambda n E is singular and is singular singular and singular and is singular and is singular and X minus lambda n X minus lambda n E tends to X minus lambda E. That implies X minus lambda E is singular. angular. That implies lambda belongs to sigma x. Hence lambda x is closed. Hence lambda x is sigma x is closed. Close. Let x belongs to capital X. X belongs to X. Let lambda be such that norm x less than lambda, then norm x less than lambda. That implies norm e minus x by lambda. Lambda. That equal to norm x by lambda less than 1. That equal to that equal to e minus x by lambda is regular. Lambda is regular. Regular. That implies by previous theorem, x minus lambda is regular. X minus lambda is regular. And see regular. That implies x belongs to O of x. Of x. Hence, lambda belongs to O of x. That implies mod lambda less than or equal to norm x. Hence prove. Hence prove. The short answer 6 marks for everybody. Next we will discuss definition. Let me the short answer type question most important. Mission. For any x belongs to x belongs to x. We define x lambda from x lambda that equal to x minus lambda u whole inverse. This defines a function from rho of x into g. Defines this defines a function from fn means function from rho of x into g. Rho of x into g. Using this definition, we'll prove one theorem. This is called resolvent equations theorem. U theorem. U lambda comma mu belongs to rho of x. Rho of x. Then x lambda minus x mu that equal to lambda mu minus mu into x lambda x mu. This is called resolvent equation. So x lambda that equal to x lambda minus mu of e x mu of mu that equal to x lambda x minus lambda e plus lambda minus mu of e x mu that equal to e plus lambda minus mu e plus lambda minus mu e plus lambda minus mu x lambda to x mu that equal to x mu plus lambda minus mu plus lambda minus mu x lambda x mu. So hence this is called Resolvent equation. Hence x lambda x lambda minus x mu equal to lambda minus mu x lambda x mu. Hence proof. This completes the proof. Short answer type most important. Right? Happy. Spectral radius. Spectral radius. Radius. Spectral radius. Definition. Let X be a complex algebra with identity. Let X be a complex algebra with identity. Complex algebra with identity. With identity. E. E. Let X belongs to let X belongs to X. X belongs means small x belongs to capital X. Then the spectral radius. Then the spectral radius. Then the spectral radius. So then the spectral radius. R of x of x. Spectral radius R of x of x is defined by rotational audio settings. Okay. R of x of x is defined by R of x equal to supremum of mod lambda such that lambda belongs to sigma of x, means spectral. Yes, spectrum. So sigma x is a non-empty. In this view theorem follows that. So most important theorem, 10 marks question. Page number 264. Page number 264. R of x equal to prove that. Question formation is prove that or show that R of x means spectral radius. R of x equal to limit n tends to infinity. Limit n tends to infinity. Norm xn whole power 1 by n. Whole power 1 by n. Okay, most important for 10 marks question. So proof. Proof. Suppose lambda belongs to pound Libra. SP means suppose lambda belongs to Libra. Means pound symbol. Libra is such that mod lambda greater than norm x. Greater than norm x. Norm x. Then lambda belongs to rho of x. Then lambda belongs to rho of x. Lambda belongs to rho of x. Further, x lambda equal to x minus lambda e. X minus lambda e whole power minus 1. That equal to lambda minus 1 x by lambda minus e whole power minus 1. That equal to minus lambda power minus 1. That equal to e minus x by lambda whole power minus 1. That equal to minus lambda power minus 1. E plus sigma n equal to 1 to infinity. N equal to 1 to infinity. X by lambda whole power n by previous theorem. Hence for any hence for any f belongs to x star belongs to capital X star and mod lambda greater than norm x greater than norm of x, we have f of x lambda that equal to minus lambda minus 1 that equal to f of a plus n equal to 1 to infinity f of x by x by lambda whole power n power n that equal to minus lambda power minus 1 f of e plus plus sigma n equal to 1 to infinity n equal to 1 to infinity f of x power n or x power n okay, into y power lambda power minus 1 minus n power minus n. Okay, next, from the proof of this theorem, as follows: pi of lambda pi of lambda equal to f of x of lambda is analytic in the region is analytic in the region the region analytic in the region mod lambda greater than r of x mod lambda greater than r of x is the Lorentz series expansion. The Lorentz series expansion the Lorentz series expansion the Lorentz series expansion Lorentz series expansion Lorentz series expansion for mod lambda greater than r of x. Spectral r of x means spectral radius. Follows that this expansion is also valid for lambda greater than r of x. Suppose r of x less than alpha less than beta. So r of x less than alpha less than alpha. That implies sigma n equal to 1 to infinity n equal to into f of x power n alpha power minus n is convergent. CGT means convergent. That implies sigma n equal to 1 to infinity 1 to infinity f of x power n divided by alpha power n. This is also convergent. That implies sigma that implies f of x is a bounded sequence. So f of x power n divided by alpha power n is bounded sequence. The bounded sequence. The sequence x power n alpha power n alpha power n is such that yeah, x power n by alpha power n is bounded for every is BDD means bounded. BDD for is bounded for every F belongs to X star. Belongs to X star. Hence, using the principle of union boundedness. Hence, using the principle of union boundedness. Principle of union boundedness. Union boundedness. Union boundedness. In functional analysis follows in FA, functional analysis follows that follows that follows that integration x power n by alpha power n is a bounded sequence in X. Is a bounded sequence in X. Bounded sequence in X. Hence, there exists hence there exists M. There exists M greater than 0 such that norm of Xn divided by alpha power n less than or equal to M so that norm Xn whole power 1 by n whole power n by n is less than or equal to M 1 by n 1 by n which shows that which shows that which shows that which shows that shows that norm Xn norm x power n whole power 1 by n less than beta for large n for large n large n. Therefore therefore limit supremum of norm Xn whole power 1 by n less than or equal to beta. This being true for a theory, true for a theory, this being true for a theory, beta greater than R of X, beta greater than R of X follows that limit supremum of norm Xn whole power 1 by n less than or equal to R of X. Thus, R of X less than or equal to limit infimum, limit infimum norm of xn whole power 1 by n, whole power 1 by n, by previous theorem, that is less than or equal to limit supremum, limit inferior, limit superior, x power n whole power norm x power n whole power n is less than or equal to r of x. So consequently, 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 norm xn, norm xn whole power 1 by n tends to r of x, means spectral radius r of x, as n tends to infinity, as n tends to infinity, tends to infinity. That is r of x means spectral radius equal to limit n tends to infinity, okay, norm x power n whole power n. So this is the most important for 10 marks question. So the formula. Next. So radical of Banach algebras. Radical of Banach algebras. Radical of Banach algebras. Radical of Banach algebras. Radical of a Banach algebra. Banach algebras. Algebras. Okay, Banach algebras. So definition. Definition. The intersection of all maximal left ideals is called the radical of x. The intersection of all maximal, all maximal ideals is called left ideals is called left ideals is called radical of x. The radical of x. Radical of x. And is denoted by capital R, and it is denoted by capital R. Next definition. Next definition. An element X belongs to capital X. X belongs to capital X. Is said to be left regular. Is said to be left regular. Left regular. Is said to be left regular. If there exists Y belongs to capital X, there exists Y belongs to capital X such that Y into X equal to E, such that Y into X equal to E, equal to E. And X is said to be, and X is said to be said to be, X is said to be right regular, right regular, right regular, right regular. There exists X belongs, Z belongs to capital X such that X into Z equal to G. Okay, a short answer like theorems. Short answer theorems. Using these definitions, we'll prove one or two theorems. Right? So let R be the radical theorem. Proof number 266. Theorem. If R be the radical of X, R be the radical of X, R be the radical of X, radical of X, and the small r belongs to capital R belongs to capital capital R. Then E minus R is left regular. E minus R is left regular. Left regular. Proof. Proof. Suppose E minus R is not a left regular. Suppose E minus R is not a left regular. Left regular. Then the set I equal to X minus XR. X minus XR such that X belongs to capital X. Is non-empty proper subset of X. Is non-empty proper subset of X. Proper subset of X. Proper subset of X. And is left ideal. And it is left ideal. And it is left ideal containing E minus R. E minus R. E minus R. Let M be maximal left ideal. Let M be a maximal left ideal. Maximal left ideal. Maximal left ideal containing I. In I. In I. Then E minus R belongs to M. E minus R belongs to M. R is substitutable. Hence, E equal to E minus R plus R or plus R, which belongs to M. So that X equal to X equal to X equal to X into E belongs to M for all X belongs to capital X. Non-X belongs to capital. Consequently, M equal to X. Consequently, M equal to X. M equal to X. A contradiction. A contradiction. Contradiction. A contradiction. M equal to capital X. A contradiction. M equal to X. A contradiction. M equal to X. A contradiction. Hence, E minus R is a left regular. Hence, E minus R is a left regular. Hence, proved. Completes the proof of theorem. Hence, proved. For short answer, 5 marks question important. So we'll discuss one more theorem. That is page number 267. Suppose x comma r belongs to capital X. Now question formation is theorem. Formation is prove that or show that. Prove that or show that x comma r belongs to capital X. Suppose x comma r belongs to capital X. Then E minus XR is regular. Then E minus XR is regular. E minus XR is regular. If and only if and only if E minus Rx is regular. Is regular. Regular. Proof. Suppose E minus XR is regular. E minus XR is regular. XR is regular. And S is the inverse. S is the inverse. S is the inverse. So that yes, E minus XR, E minus XR that equal to E. Yes, E minus XR that equal to E. That equal to E minus XR XR into S. Then E minus Rx, E minus Rx, E minus RSX, E plus RSX that equal to E into E plus ERSX, ERSX, ERSX minus RXE, RXE minus RX, RSX, RX, RSX, RSX that equal to E plus RSX, RSX minus RX, RX minus RX, RSX, X, RSX that equal to E minus RX, E minus RX plus taking R is common. R is common. S minus X R S into X. X is also can take. That equal E minus Rx plus Rex plus Rex. That equal to E minus Rx plus Rx. Because E is the identity element, no? These two goes to 0. That equal to E. So E. Similarly, ERSX, E plus RSX into E minus Rx, that equal to E. So hence E minus Rx is regular with regular with is regular with E plus RSX, E plus RSX as its inverse, inverse, as its inverse. Okay. Next, semi-radical axis. Definition: semi-radical axis. Semi-radical radical axis. Okay, semi-radical algebra. Definition. Definition. The complex Banach algebra X. Let's Banach algebra X. Algebra X algebra X. Complex Banach algebra X with identity E. With identity E. Identity E is said to be semi-simple. Said to be semi-simple. 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 If its radical are equal to, if its radical are equal to 0, is zero ideal. Is zero ideal. Zero ideal. So here on page number 268, uh, theorem. Theorem. 14.6.4. Take it as 1 mark. Uh, for 10 marks. What is the theorem? L is a closed two-sided ideal in X. But then the quotient space X by T is Banach algebra. What is the theorem most important for 10 marks theory? Uh, don't have time to explain. So I need to close. That's why if L is a closed two-sided ideal in X, then the quotient space X by I is a Banach algebra. Orally I'll explain. So we know that functional analysis X by L is a complex Banach space with a norm defined. Norm X plus L to the infimum of norm X plus Y such that Y belongs to I. So that is X plus I, Y plus I equal to XY plus I for all X comma Y because I is the identity. So X by I plus is a ring with epsilon plus I as the identity. So norm E plus I that implies infimum of or norm E plus Y such that Y belongs to I less than or equal to norm E since 0 belongs to I that equal to 1. For X comma Y belongs to norm X plus Y Y plus I that implies norm XY plus I that is infimum of XY plus A belongs to I is less than or equal to infimum of norm X plus B Y plus Y plus C uh, Y plus C such that B comma C belongs to I. Less than or equal to, it's less than or equal to, hmm? Less than or equal to, as the infimum of X plus B, this infimum X plus B, B belongs to I. Infimum of Y plus C, C belongs to I. So norm X plus I, Y plus I. X plus I is a Banach algebra with E minus E plus I as identity. Okay, I explained orally do that's one. Huh? So I'm leaving. Thank you very much. We'll meet next class. We'll meet next class on 8th of March. Thank you.